This video is actually a section of a course. This section includes the following lessons. First, conditional statements. If, else, executing code based on a condition. Second, conditional statements. Else if, handling multiple conditions. Third, conditional statements. Switch case. Multi-way branching based on a variable's value. Fourth, loops. For loop. Iterating a specific number of times. Fifth, loops. While loop. Iterating as long as a condition is true. Sixth, loops. Do-while loop. Ensuring the code block executes at least once. Seventh, loop control, break. Exiting a loop. Eighth, loop control. Continue. Skipping the current iteration and moving to the next. Ninth, exercises to practice programming thinking skills. No answers. This lesson does not include the answers. 10th, solving exercises. Don't see this video if you've not tried to solve. Okay, let's get started. Welcome to Section 3, Control Structures. In Section 2, we learned how to store data and how to ask questions. We know how to check if score is greater than 100 and get the answer 1, true, or 0, false. But so far, our program does nothing with that answer. Our code just runs from the top to the bottom, one line after another, and then ends. It has no brain, can't make a choice. Today, that changes. We are going to learn how to tell our program, if this condition is true, then execute this block of code. Otherwise, do that. This is the single most fundamental concept in all of programming. Welcome to Lesson 3.01. We are starting our journey into control structures with the most important one, the if-else statement. An if statement is a fork in the road for your program. It's how you give your code the power to make decisions. This lesson is simple. We'll learn the if statement, the main path. We'll learn the else statement, the otherwise path. First, the if statement, the main path. The if statement is simple. It checks a condition, and if that condition is true, it runs the code inside the curly braces. The syntax looks like this. The condition is any expression from Section 2 that gives a true, 1, or false, 0 result. Let's use an example. Checking if a user is old enough to vote. The code in the curly braces. This code only runs if the condition, age is greater than or equal to 18, is true. Output will be, you approach the voting booth. You are allowed to vote. You have left the voting booth. Because age is 20, 20 is greater than or equal to 18 is true, 1. So the code block runs. But what if the age is 15? If 15 is greater than equal to 18, is false, 0. The program skips the entire code block inside the curly braces. Output will be, you approach the voting booth. You have left the voting booth. That's a bit anticlimactic. We need a way to handle the false case. Second, the else statement, the otherwise path. The else statement is the safety net. Catches any case that the if statement didn't. You can't have an else without an if. The syntax looks like this. Let's fix our voting program. Let's try the false case. This block runs if the condition is true. This block runs if the condition is false. Output will be, you approach the voting booth. You are too young to vote. You have left the voting booth. This is a perfect either or choice. The program must run one of these two blocks, but it can never run both. Third, the single line trap. One last thing. C allows you to write an if statement without curly braces. If and only if you have one statement to execute. This is dangerous and considered bad practice. My advice, always use the curly braces. It makes your code safe and easy to read. You now have the power to make a two-way decision. If this, else that. But what if you have more than two choices? What if you want to check If the grade is A, print excellent. Else if the grade is B, print good. Else if the grade is C, print average. Else print fail. We need a way to chain multiple if statements together. Click on the next video to learn how to handle multiple conditions in Lesson 3.02. Conditional Statements. Else if. In the last lesson, we gave our program the power to make a decision. If a condition is true, else otherwise do something else. That's a simple two-way choice. But the real world rarely offers just two options. Imagine a grading system. A student gets 90 to 100, grade A. A student gets 80 to 89, grade B. A student gets 70 to 79, grade C. A student gets less than 70, fail. This is 4 different outcomes. How do we structure our code to check all these possibilities efficiently? If we use a simple if followed by a simple else, we can only handle 2. We need a way to check a second condition only if the first one failed. Welcome to Lesson 3.02. Today, we are learning the else if statement. The else if is the intermediate choice. It links the first if and the final else, allowing us to create a chain of possibilities. It creates a single, sequential structure where only one outcome can ever be executed. This lesson will focus on the structure of the if-else chain, the critical importance of order in your conditions. First, the if-else chain. The else-if statement is a checkpoint. It says, the first condition failed, so let me check this next condition. The full decision chain looks like this. Let's build the grading system example. Check this only if score was less than 90. Check this only if score was less than 80. Final fallback if all above conditions failed, score was less than 70. The program starts at the first if. Is 85 greater than or equal to 90? False. The program moves on. It hits the first else if. Is 85 greater than or equal to 80? True. The program executes the code block printf grade B. Good work. Crucially, once one block is executed, the entire chain is finished. The program skips the remaining else if and the final else. The output is simply, grade B, good work. This is the power of the chain, mutually exclusive execution. Only one path runs. Second, the critical importance of order. This is the number one mistake beginners make with else if. The order of your conditions matters because C checks them sequentially. Look at our example again. We checked for 90 first, then 80. What if we reversed the order? The program starts. Is 95 greater than or equal to 70? True. The program executes printf grade C, average. The program stops. The grade 95 is incorrectly assigned a C. The rule of order. When checking ranges, like grades, you must always check the most restrictive condition, highest number, first, and work your way down. Third, why else if is better than multiple independent ifs? You might ask, why not just use a bunch of separate if statements? All these blocks are checked independently. 85 is greater than or equal to 80 is true. 85 is greater than or equal to 70 is true. Output will be grade B grade C. This is broken. The student gets multiple grades. By chaining them with else if, we guarantee that once the student meets the highest criteria, the program stops checking the others. The if, else structure gives you the power to handle complex, multi-layered decisions perfectly. It is ideal when you are checking ranges or overlapping conditions. But what if you are checking for a single, exact value? For example, if the day is Monday, run code A. If the day is Tuesday, run code B. If the day is Wednesday, run code C. Using else if for 20 different exact days can become long and messy. C has a cleaner, dedicated tool for checking one variable against many distinct values. Click on the next video to learn about a powerful alternative for multi-way branching. Lesson 3.03, Conditional Statements. Switch case. In the last lesson, we successfully used the if-else chain to handle multiple outcomes like a grading scale. That structure is perfect for checking ranges, such as, is the score greater than 90? But what if your program only needs to check for exact, specific values? Imagine you're writing a program for a simple menu. If the user enters 1, run the start game function. Else, if the user enters 2, run the load game function. Else, if the user enters 3, run the options function. And so on for 10 different choices. Using a long else if chain for every single one of those exact numbers is tedious and inefficient. There is a more elegant, dedicated tool for this job. Welcome to Lesson 3.03. Today, we are mastering the switch case statement. The switch case structure is a special type of conditional statement designed specifically for multi-way branching based on a single variable's exact value. It's like a jump table. It takes the value of a single variable and immediately jumps to the correct block of code. This lesson will focus on the fundamental syntax of switch and case, the absolutely critical role of the break keyword, the optional but important default case. First, the switch case syntax. The switch statement takes a single variable, usually an integer or char, and compares it against a list of possible case values. Let's use our menu example. Second, the critical importance of break. If you forget the break keyword, your program will have a serious bug called fall-through. The break keyword tells the program, I found the correct case. Now immediately exit the entire switch block. Let's remove the break from case 1. If choice is 1, output will be starting a new game, loading saved game. The program finds case 1, executes its code, and because there is no break, it falls through and executes the code for case 2 as well. This will continue until it hits a break or reaches the end of the switch. Rule: always include a break after the code for each case, unless you specifically want the fall-through behavior, which is rare. Third, the default case. The default case is like the final else in an if-else-if chain. It's optional but highly recommended. The default block executes if the variable being switched on does not match any of the defined case values. It's your error handling or general fallback case. In our example, if choice was 99, the default case would run, printing invalid choice. You do not need a break after default since it is the last item in the switch block. Fourth, switch case versus if-else-if. When should you use which? About if-else-if chain. Use case: ideal for checking ranges or complex conditions, e.g., score is greater than 90, age is greater than 18, and a citizen is equal to 1. Flexibility: highly flexible. Conditions can be complex expressions. Readability: good for few conditions, but messy for many. About switch case statement. Use case: ideal for checking one variable against many exact values, e.g., day is equal to 1, menu is equal to a. Flexibility: limited. Can only check against constants, fixed values, not variables or ranges. Readability: excellent for many exact values. Rule of thumb: if you need to check if a value is greater than something, or if you need to combine conditions with an operator or operator, use if-else-if. If you just need to check if a variable equals A, B, or C, use switch case. You now have two powerful tools for making decisions: if-else-if for ranges and complex logic, and switch case for multi-way exact value branching. You can make your program jump to the right piece of code. But what if you need your program to perform an action repeatedly? For example, print hello exactly 100 times. or keep asking for a password until the user gets it right. To do that, we need loops. Click on the next video to start learning the first looping mechanism. Lesson 3.04. Loops. For loop, which is used for iterating a specific number of times. In the last few lessons, we taught our program how to make decisions using if, else, if, and switch. That's powerful. But what if you need your program to perform an action many times? Imagine you're coding a game, and every time a player levels up, you need to print a banner 50 times that says, "Congratulations!" Would you manually type the printf statement 50 times? No, that's slow, boring, and prone to errors. Programmers never do repetitive tasks manually. We tell the computer to do it for us. We use loops. Welcome to Lesson 3.04. Today, we are learning the first type of loop in C, the for loop. A for loop is designed specifically for situations where you know exactly how many times you need to repeat a block of code. For example, I need to run this code 10 times, or I need to process items from index 0 to index 9. The for loop is often called the counted loop because it relies on a counter variable. This lesson will focus on dissecting the three essential parts of the for loop syntax, creating our first controlled, repetitive block of code. First, the three sections of the for loop. The for loop is arguably the most intimidating piece of syntax for C beginners because it packs three separate instructions into one line, separated by semicolons. The syntax looks like this. Let's break down the classic example, looping 10 times. Part 1. Initialization, integer I equals 0. This section runs only once at the very beginning of the loop. We use it to create and initialize the control variable, the counter. By convention, we often use I for index or iterator. In this case, we start our counter I at 0. Part 2. Condition, I is less than 10. This is the test. It is checked before every iteration. As long as this condition evaluates to true 1, the loop's code block will execute. As soon as this condition evaluates to false 0, the loop stops immediately. In this case, the loop will run as long as I is less than 10. Part 3. Update, I increases by 1. This section runs after the code block has executed, at the end of every iteration. We use it to modify the control variable. Here I++, which is a shortcut for I equals I plus 1, increments our counter by 1. Second, the execution flow. Let's trace the loop above. Step 1, start. Action, create I, initialization. Assign 0 to I, condition, true 0 is less than 10. Output, loop iteration, 0, update. I increases by 1, I becomes 1. Step 2, action, check condition, true 1 is less than 10. Output, loop iteration, 1, update. I increases by 1, I becomes 2. Step 10, action, check condition, true, 9 is less than 10. Output, loop iteration, 9, update. I increases by 1, I becomes 10. Step 11, stop, action, check condition, false, 10 is less than 10, and the loop stops. The loop runs exactly 10 times, counting from 0 up to 9. Third, common variations. You don't always have to count up by 1. You can count down or skip numbers. Example A, counting down. This loop runs 5 times, counting 5, 4, 3, 2, 1. Example B, skipping numbers. This loop prints all even numbers from 0 to 20. Key takeaway. The power of the for loop is that you have total control over the start, the stop condition, and the step size all on a single line. The for loop is your best friend when you know the exact count needed, e.g., looping through all 10 items in a list, or running a simulation 1,000 times. But what about situations where you don't know how many times the loop should run? For example, keep asking the user for a password until they get it right. Keep reading data from a file until you reach the end. In these cases, the loop needs to run as long as a condition remains true, not based on a specific count. Click on the next video to learn the second essential looping mechanism. Lesson 3.05. Loops. While loop, the condition-controlled loop. In the last lesson, we learned the for loop, the perfect tool when you know exactly how many times you need to repeat an action. It's the counted loop. But let's look at two real-world programming scenarios. Password check. You need to keep asking the user for a password until the input matches the correct value. You don't know if it will take 1 try or 100 tries. Reading file. You need to keep reading lines of text from a file as long as you haven't reached the end of the file. You don't know the file's length. In these cases, you cannot use a for loop because you don't have a fixed count. You need a loop that continues as long as a condition remains true. Welcome to Lesson 3.05. Today, we are learning the while loop, the second fundamental looping mechanism. The while loop is the condition-controlled loop. It is the simplest and most direct way to express repetition. While this statement is true, keep doing this block of code. You might hear people say that anything you can do with a for loop, you can do with a while loop, and that's true. The difference is the readability and intent. First, the while loop syntax. The syntax for the while loop is deceptively simple compared to the for loop. It only requires a condition inside its parentheses. The syntax looks like this. However, to avoid an infinite loop, a trap we'll discuss soon, the three essential parts of any loop must still exist. They are just handled separately. Initialization. Done before the while loop starts. Condition. Done inside the while parentheses. Update. Done inside the loop's code block. Let's convert our classic 10-time counter into a while loop to see the structure. Initial check. The loop starts. Is I less than 10? 0 is less than 10? True. Iteration 1. Code runs. I is increment to 1. Next check. Is I less than 10? 1 is less than 10? True. This continues until final check. Is I less than 10? 10 is less than 10? False. The loop immediately terminates. Second, the danger, the infinite loop trap. The single biggest danger with the while loop is forgetting the update step. Part 3. If the condition is initially true and you don't put code inside the loop to make it eventually false, the loop will run forever until you forcefully stop your program. This is an infinite loop. The key to a safe while loop is ensuring that the code block guarantees that the condition will eventually become false. Third, real-world use. Sentinel-controlled loop. Password example. The while loop shines in situations where the loop is controlled by user actions or external factors, often called a sentinel-controlled loop. Let's look at the password check scenario. In this case, the condition is guess is not equal to secret underscore code. The update is scanf%d, ampersand guess inside the loop, which asks the user for a new guess. The loop keeps running until the new guess satisfies the condition. Fourth, for versus while choosing the right tool. For loop, when to use. When you know the exact number of iterations needed. Example, printing a grid of 10 by 10, iterating over an array of fixed size. While loop, when to use. When you loop as long as a condition is true, count is unknown. Example, waiting for user input, reading a file line by line, waiting for a server response. You now have a powerful, flexible tool in the while loop. It checks the condition before running the code block. But what if you have a scenario where you want to guarantee that the code block runs at least once, and then you check the condition to see if it should run again? This is perfect for things like menus, where you always want to display the menu at least once. Click on the next video to learn about the slight but important variation. Lesson 3.06. Loops. Do-while loop, the do this first, then check loop. In the last lesson, we built an important piece of code, a password checker using the while loop. Remember the problem. To make the password checker work with a while loop, we had to ask the user for their guess twice. Once before the loop to set the initial condition, and once inside the loop to update the condition. This is redundant and less efficient. Why? Because the while loop is a pretest loop. It always checks the condition before running the code block. What if we could guarantee that the code block, the part that asks for the password, runs at least once and then we check the condition? Welcome to Lesson 3.06. Today we are learning the third and final basic loop structure, the do-while loop. The do-while loop is the answer to the problem we just saw. It is a post-test loop. It does the code block. It then checks the while condition to see if it should repeat. This means the code inside the curly braces is guaranteed to execute at least once, even if the condition is immediately false. First, the do-while loop syntax. The syntax separates the action, do, from the condition, while. Let's rewrite our password checker using do-while. Guaranteed run. The program immediately executes the do block, prompting the user and getting the guess. First check. After running, it checks the while condition. If the guess was correct, the condition is false and the loop terminates. If the guess was incorrect, the condition is true and the loop repeats, running the do block again. The result is cleaner code because we eliminated the redundant input call that the while loop required outside its block. Second, the unique advantage, execution guarantee. Let's look at the key difference between while and do-while. Scenario A, while loop, pretest. Output, nothing. The code block never runs. Scenario B, do-while loop, post-test. Output, this prints once. Then the condition is checked. Key takeaway. If your program requires the user to interact or input data before you can possibly check if the loop needs to run again, use the do-while loop. Common uses include data validation, displaying menus, or running interactive prompts. Third, the required semicolon trap. The last major point is a common syntax error. In the for loop and if statement, you never put a semicolon after the control line. However, the do-while loop requires a semicolon after the while condition because it is the actual end of the control structure statement. Forgetting this semicolon will result in a compiler error. You now know all three fundamental loop types. For definite iteration, you know the count. While, for indefinite iteration, based on a condition, checked first. Do-while, for indefinite iteration, based on a condition, checked last. Guaranteed one execution. These loops let you repeat code. But what if you are 500 iterations deep into a for loop and suddenly a critical error occurs, like a file disappears, and you need to immediately stop the loop? Or what if you just want to skip one bad piece of data and continue to the next iteration? We need special keywords to control the loop's execution. Click on the next video to learn the powerful loop control statements, starting with Lesson 3.07. Loop control. Break, which allows you to exit a loop at any time. You now know how to run code repeatedly using for, while, and do-while loops. This is huge, but loops are rigid. What if you are running a for loop that is designed to count from 1 to 1000? But on the 50th count, you find a critical error like the user disconnected or a necessary file went missing. If you don't do anything, the program will continue looping 950 more times, wasting time and possibly causing more damage. We need a way to hit the emergency stop button on our loop. We need to exit the loop immediately, regardless of what the condition says. Welcome to Lesson 3.07. Today, we are learning the first of two critical keywords for advanced loop control, the break statement. The break keyword's job is simple and absolute. It immediately terminates the nearest enclosing loop or switch statement. As soon as the program encounters break, it completely stops the loop and jumps to the very next line of code after the loop structure. This lesson will focus on using break to exit a counted loop early, using break to solve problems in infinite loops. First, using break in a for loop, early exit. The most common use of break is to exit a loop early when a specific, unplanned event occurs. Let's imagine a loop that searches a database, simulated here by checking numbers. We only need to search up to number 5, but the loop is designed to go to 10. The loop runs for I equals 1, 2, 3, 4. When I hits 5, the if I is equal to 5 condition becomes true. The break statement executes. The program immediately jumps past the closing brace of the for loop, ignoring the rest of the planned iterations, 6 through 10. The output stops abruptly after target found and immediately prints search complete. Second, using break to control an infinite loop, sentinel control. We learned that the while loop is condition controlled. A sophisticated way to use loops is to create a loop that is technically infinite, and then use a conditional break statement to control the exit. This is very common when you are reading user input and don't know when the user will signal they are finished, the sentinel value. We can create an infinite while loop by simply making the condition always true, while 1. The loop starts, while 1. The user enters a number. If the number is 5, the if number is equal to 0 is false, the break is skipped, and the loop continues. If the user enters 0, the if becomes true, the break executes, and the program jumps out to the final printf. This structure is highly flexible and gives you precise control over exactly when the loop terminates. Third, review the switch and break connection. Remember back in Lesson 3.03, we introduced break in the context of the switch case statement. The function of break is identical, to immediately exit the enclosing structure. Whether that structure is a for, while, do while, or switch, the keyword's job is to stop execution and jump to the line immediately following that structure. The break keyword is powerful because it lets you prematurely stop a loop. But what if you don't want to stop the entire loop? What if you're processing 100 pieces of data, you hit one corrupt piece of data, and you just want to skip that one bad piece and move immediately to the next item? Using break would stop the whole process. We need a way to skip just the current iteration and immediately go back to the top of the loop. Click on the next video to learn the second loop control keyword. Lesson 3.08. Loop control. Continue, which allows you to skip to the next iteration. In the last lesson, we learned about the break statement, our emergency stop button. It lets you exit a loop immediately, no matter what the loop condition says. That's perfect if a critical error occurs. But what if the error is minor? Imagine you are looping through a list of 100 students to calculate their grades. On student number 50, you find that their score data is corrupted, a negative number, for example. If you use break, you stop the calculation for the remaining 50 students. That's inefficient. You don't want to stop the whole loop. You just want to say, skip this one bad student and move immediately to student number 51. We need a way to skip the rest of the code in the current iteration and immediately jump to the next one. Welcome to Lesson 3.08. Today, we are learning the second loop control keyword, the continue statement. While break terminates the entire loop, the continue keyword only terminates the current iteration of the loop. When the program encounters continue, it immediately skips all remaining code in the loop block. For a for loop, it jumps straight to the update section, I++. For a while or do-while loop, it jumps straight to the condition check. This lesson will focus on, first, using continue to skip invalid data, data filtering. Second, understanding the execution flow of continue in different loop types. First, using continue to skip invalid data. The main use of continue is to filter out unwanted or invalid data and save processing time by avoiding unnecessary operations. Let's use a for loop to print all numbers from 1 to 10, but we want to skip the number 5. The loop runs for I equals 1, 2, 3, 4. Everything is normal. When I hits 5, the if I is equal to 5 condition is true. The continue statement executes. The program immediately skips the printf processing item, %d new line, I line below it. It jumps straight to the update section, I++, setting I to 6. The loop resumes normally for I equals 6, 7, 8, 9, 10. The output clearly shows that processing item 5 is missing. Second, the trap placement in while and do-while loops. The placement of continue inside a while or do-while loop is extremely dangerous if you forget one thing: the update step. Remember that while and do-while loops require you to manually put the counter update, I++, inside the loop block. I is 1, 2, prints normally. I hits 3, continue executes. The program skips the I++ line. It jumps back to the while, I is less than or equal to 5, condition check. Since I is still 3, the condition is true. It runs the loop again, hits continue again, and skips the I++ again. The value of I is permanently stuck at 3. This is an infinite loop. The rule: if you use continue in a while or do-while loop, you must ensure that the variable controlling the loop's condition is updated before the continue statement executes. A safer design for the while loop would require restructuring the logic or wrapping the code that might be skipped in an if block, ensuring I++ runs every time. Third, summary. Break versus continue. Break, function. Exit the loop entirely. Effect: stops the entire process and moves to the code after the loop. Analogy: hitting the emergency stop button. Continue, function. Skip the current iteration. Effect: skips the remaining code in the loop block and immediately starts the next iteration. Analogy: pressing the skip button on a video playlist. You now have the tools to control the flow of your program. Decisions: if-else-if switch case. Repetition: for while do-while. Control: break, continue. With these things, you can start solving many problems. The next step is the most important part of becoming a programmer: practice. Click on the next video to receive your final set of challenges for this section. Lesson 3.09. Exercises to practice programming thinking skills. No answers. You should try them yourself before moving to the solutions. Conditional Statements. Part 1 Basics. Exercise 1. Write a program that inputs 2 integers. Find the largest value. Exercise 2. Write a program that inputs 3 integers. Find the smallest value. Exercise 3. Write a program that inputs student scores including attendance, 10%, midterm, 30%, and final exam, 60%. Calculate the average score and classify it according to the following rules. Average score is less than 5, so grade D. Average score is greater than or equal to 5 and less than 7, so grade C. Average score is greater than or equal to 7 and less than 9, so grade B. Average score is greater than or equal to 9, so grade A. Exercise 4. Write a program to solve a linear equation of the form x plus b equals 0. Exercise 5. Write a program that takes 2 values, month and year, as input. Output the corresponding number of days in that month. Hint: A leap year is a year divisible by 4 and not divisible by 100, or divisible by 400. Months with 30 days, 4, 6, 9, 11, 31 days, 1, 3, 5, 7, 8, 10, 12. February is a special month. 28 days. Non-leap year, 29 days. Leap year. Part 2, Advanced. Exercise 1. Input a positive integer with at least 1 digit and at most 3 digits. Read that positive integer in words. Part 3, Analytical Thinking, Reasoning. Exercise 1. Write a program that takes 4 arbitrary real numbers as input. Find the maximum value. Condition. The program can only use a maximum of 2 variables. Exercise 2. No knowledge of section 3 required. Write a program that takes 2 positive integers a and b as input. Find the maximum value. Conditional statements are not allowed. Exercise 3. No knowledge of section 3 required. Write a program that takes 2 variables, month and year, as input. Output the number of days in that month. Conditional statements and branching structures are not allowed. Loop. Part 1 Basics. Exercise 1. Input a positive integer n. Calculate the sum s, n, according to the following formula. Exercise 2. Input a positive integer n. Calculate the product s, n, according to the following formula. Exercise 3. Input a positive integer n. Calculate the sum s, n. Exercise 4. Input a positive integer n. Output all even values in the range from 1 to n. Exercise 5. Input a positive integer n. List all the divisors of the positive integer n. Exercise 6. Input a positive integer n. Calculate the sum of the divisors of the positive integer n. Part 2, Advanced. Exercise 1. Input a positive integer n. Output the digits of the positive integer n. Hint. Use the modulo operator and integer division by 10. Exercise 2. Input a positive integer n is greater than 0. Output the even digits of the positive integer n. Hint. Use the modulo operator and integer division by 10. Exercise 3. Input a positive integer n. Calculate the sum s, n. Exercise 4. Input a positive integer n. Calculate the sum s, n. Part 3, Logical Reasoning. Exercise 1. The sock problem. You have n pairs of socks. Every day you wear 1 pair and then throw it away. Every m days your mother buys you a new pair of socks. How many days will it take until you run out of socks to wear? Exercise 2. Input a positive integer n with a maximum of 10 digits. Write a program to read that number n in words. Conditional Statements. Part 1 Basics. Exercise 1. 1. The problem review. Let's begin with our first problem. Exercise 1. Write a program that inputs 2 integers, a and b. Find the largest value. This is a classic comparison problem. The computer needs to make a clear two-way decision. Is a larger than b, or is b larger than a? This immediately tells us we must use the fundamental if-else structure from Lesson 3.01. 2. Required setup. Input. First, we need to handle the input. We need 2 integer variables, a and b, and we need to use scanf to get the values from the user. 3. The core logic if-else. We are looking for the largest value. The most straightforward way to solve this is to ask, is a greater than or equal to b? We use the comparison operator, greater than or equal to. Using the or equal to part is critical because if the user enters the same number for both, like A equals 2 and B equals 2, the condition A is greater than or equal to B is true, and the program correctly outputs the number 2. 4. Review and final solution. Let's trace the logic with the examples. Example 1. Input A is 3, B is 7. The condition is checked if 3 is greater than or equal to 7. This is false. The program skips the if block and runs the else block. Output: the largest value is 7. Correct. Example 2. Input A is 2, B is 2. The condition is checked if 2 is greater than or equal to 2. This is true. The program runs the if block. Output: the largest value is 2. Correct. This solution uses only the core concepts: variable declaration, scanf, for input, the if-else control structure, and the is greater than or equal to operator. Simple, clean, and efficient. 1. The problem review. Next up is exercise 2. Write a program that inputs 3 integers, A, B, and C. Find the smallest value. This is a step up from the previous problem because we now have 3 variables to compare, meaning more possibilities. We are looking for the minimum value. Just like before, we start with the setup. 2. Required setup, input. We need 3 integer variables, A, B, and C. 3. The core logic, the chained if-else approach. To find the smallest value, we can simply check each variable against the other 2. We ask 3 sequential questions, forming a single chain that guarantees only one path is executed. Is A the smallest? If not A, is B the smallest? Else if not A and not B, then C must be the smallest. Else. This is the most logical and efficient way to solve it with our current toolset. 4. Review and key takeaway. Let's trace the logic with one of the examples. Example. Input A is 4, B is 5, C is 2. The condition if A is less than or equal to B and A is less than or equal to C is checked. 4 is less than or equal to 5 and 4 is less than or equal to 2. This evaluates to true and false, which is false. The program skips to the else if block. The condition else if B is less than or equal to C is checked. 5 is less than or equal to 2. This is false. The program skips to the final else block. Output: the smallest value is 2. Correct. The key takeaway here is the power of the logical and operator. By combining A is less than or equal to B and A is less than or equal to C, we can check multiple conditions simultaneously to isolate the true minimum in a single, elegant control flow structure. 1. The problem review. Our third exercise is a practical application of C programming. Write a program that inputs student scores, attendance 10%, midterm 30%, final exam 60%. Calculate the average score and classify it according to the defined rules. This problem requires 2 stages. First, arithmetic for the weighted average, and second, control structures to determine the final grade. 2. Setup and the data type rule. Because we are dealing with percentages, the final average score will certainly be a decimal number. Therefore, we must use the float data type for all our scores and the final average score. 3. The classification logic order is critical. We have 4 possible outcomes: grades A, B, C, D. So the if-else chain is perfect. Remember the rule from lesson 3.02. Always check the most restrictive condition first. Grade A, score 9 and above, is the most restrictive, so we start there. 4. Review and final code. Let's trace one of the tricky examples. Attendance is 8, midterm is 7, final exam is 9. The calculation is 8 times 0.1 plus 7 times 0.3 plus 9 times 0.6 equals 0.8 plus 2.1 plus 5.4 equals 8.3. Average score is 8.3. If 8.3 is greater than or equal to 9, false. Else if 8.3 is greater than or equal to 7? True. The program stops here and outputs. Final grade, grade B. Correct. The structure works perfectly because the if-else chain ensures that only the highest matching grade is ever selected, giving us a clean and correct solution. Exercise 4.1. The problem review. Our final challenge in this section is exercise 4. Write a program to solve a linear equation of the form ax plus b equals 0. This problem is primarily about conditional logic, not just calculation. The program must analyze the coefficients a and b before it attempts to calculate the solution. This is a perfect case for the if-else structure. 2. Setup and data types. Since the result of division, the solution for x, will almost certainly be a decimal number, we must use the float data type for the coefficients a and b, and the solution x. 3. The core logic if-else chain. We must check the edge cases first. The most problematic cases are when a equals 0. Case A. Infinitely many solutions. A equals 0 and b equals 0. If both a and b are 0, the equation becomes 0x plus 0 equals 0. Any value of x satisfies this, so we have infinite solutions. We check this first because it is the most restrictive and complex exception. Case B. No solution. A equals 0 and b is not 0. If a is 0 but b is any other number like 2, the equation is 0x plus 2 equals 0, or 2 equals 0. This is a contradiction, meaning there is no value of x that can solve it. We use else if to check this case next. Case C. Unique solution. A is not 0. If neither of the 0 cases for a were true, a must be a non-zero number. This guarantees a single, unique solution. We use the final else block for this, and solve for xx equals minus b over a. 4. Review and final code. Let's trace the logic with the examples. Example 1. A is 1, b is 2. If 1 is equal to 0 and 2 is equal to 0? False. Else if 1 is equal to 0. False. Runs the else block x equals minus 2 over 1. So x is minus 2.00. Correct. Example 3. A is 0, b is 0. If 0 is equal to 0 and 0 is equal to 0? True. Output. Infinitely many solutions. Correct. The key to solving algebraic problems like this is using logical and to capture the special case where both a and b are 0, and structuring the if-else chain to deal with the exceptions before the general case. Exercise 5.1. The problem review. This is exercise 5. Write a program that takes two values, month and year, as input and outputs the corresponding number of days in that month. This is a multi-layered logic problem. We have a general rule for most months, and a special nested rule for February that depends on the year being a leap year. This is a great exercise for structuring complex if-else statements. 2. Required setup. Input. Since months and years are always whole numbers, we'll use the integer data type for both. 3. The core logic, the leap year check. We can't determine the days in February without first checking if the year is a leap year. This is a complex condition that uses logical and illogical, or a year is a leap year if it is divisible by 4 and not divisible by 100, or it is divisible by 400. We'll use a Boolean-like integer variable isLeap to store the result of this complex check. 4. The core logic, the month check. Since the month can be one of 12 distinct values, a switch case structure is the cleanest way to handle the logic. 5. Key takeaway. This problem demonstrates the power of combining structures. We used a complex set of logical operators to create a single Boolean variable, isLeap. We then used a switch case for efficient multi-way branching, and inside one of the cases, case 2, we used a simple if-else to resolve the final number of days. 1. Introduction. This is a logic problem in our series, reading a number from 1 to 999 in words. Our strategy is a three-part breakdown using mathematical operators. Extract and process hundreds, n over 100. Extract the remainder, n mod 100. Use extensive if-else chains to handle tens, 20 to 99, teens, 10 to 19, and ones, 1 to 9. 2. Full C code implementation. Three. Step-by-step logic explanation. Step 1. The hundreds check. We start by isolating the hundreds digit using hundreds_digit equals n over 100. We then run a long if-else, if chain to print the word 100 through 900. Crucially, we then calculate the remainder, last_2_ equals n mod 100. If this remainder is not 0, meaning the number is not exactly 100, 200, etc., we print the connecting phrase and Step 2. The special case teens, 10 to 19. The numbers 10 through 19 are exceptions. 10, 11, 12, 13, etc. We use a separate if block to check specifically for this range. If last_2_ is greater than or equal to 10 and last_digits is less than or equal to 19. Inside this block, a dedicated chain of if-else if prints these unique words, preventing them from being broken down into tens and ones. Step 3. Tens, 20 to 99, and ones. If the number is not a teen, we proceed to handle all numbers from 20 up to 99, and finally the single digits, 1 to 9. We separate the tens and ones. Tens_digit equals last_2_ over 10 and ones_digit equals last_2_ mod 10. A long if-else if chain prints the tens word 20 through 90. If ones_digit is not 0, we print a hyphen and then use another if-else if chain to print the final ones word 1 through 9. Case 3, single digits, 1 to 9. This case is for the case when you enter a one-digit number. This multi-step conditional breakdown ensures every number from 1 to 999 is converted correctly, without needing complex data structures. 1. The problem review. This is an excellent problem. Exercise 1. Input for arbitrary real numbers. Find the maximum value. Condition. The program can only use a maximum of 2 variables. The key to solving this is recognizing the analytic trick. We don't need 4 variables to store the inputs if we process them sequentially and only need to keep track of the current maximum. 2. The analytical trick and variable setup. We are limited to 2 variables. Here is how we will use them. Number. This variable will be reused to hold each of the 4 inputs one after another. A, B, C, D. Max_value. This variable will store the largest number found so far as we check the inputs sequentially. Since the inputs are real numbers, we must use the double data type, lesson 2.02. 3. Step-by-step logic implementation. Step 1. Initialize the maximum, input A. We must read the first number A and use it to initialize our max_value. Step 2. Check input B. We reuse the number variable to read the second input, B. We then use a simple if statement, lesson 3.01, and a comparison operator, greater than, lesson 2.06, to check if the new number is greater than our current maximum. Step 3. Check input C. We repeat the exact same logic for the third number, C. The number variable is overwritten again. Step 4. Check input D and output. Finally, we repeat the logic for the fourth number, D. After this final check, the max_value must contain the absolute maximum of all 4 inputs. 4. Conclusion and key takeaway. This solution uses only the 2 required variables, number and max underscore value. The key to solving this kind of constraint problem is reusing variables and processing data iteratively. You don't need to store all the data simultaneously. You just need to keep track of the most important result found so far. This kind of logical thinking is what separates good coders from great coders. Exercise 2. 1. The problem review. This is the ultimate test of your Section 2 knowledge. Exercise 2. Input two positive integers a and b. Find the maximum value. Rule. Conditional statements, if, else, switch, are not allowed. 2. The analytical trick, using 1 and 0. The core concept is this. In C, a comparison operator, like is greater than or equal to, always returns either 1, true, or 0, false. We can exploit this property by using the result of a comparison as a multiplier. Any number multiplied by 1 is itself. Any number multiplied by 0 is 0. This means we can design an expression where the non-maximum number is guaranteed to be multiplied by 0 and the maximum number is guaranteed to be multiplied by 1. 3. Step-by-step logic implementation. We need 4 integer variables, a, b, and 2 temporary variables, max underscore a and max underscore b, to hold the result of the multiplication, plus the final max. For logic trace, let's trace how the program makes the choice without using any if statements. In every scenario, the logic works. The value we do not want is cancelled out by being multiplied by 0, and the correct maximum value remains multiplied by 1. 5. Conclusion and key takeaway. This incredible mathematical shortcut proves that in C, you can often replace complex control flow structures with creative use of operators. While in professional code, we almost always prefer the readability of the if-else statement. 1. The problem review and core difficulty. This problem asks us to find the number of days in a given month and year, but with a huge constraint. No conditional statements, if, else, switch are allowed. Normally, this requires 3 branches, 31 days, January, March, May, July, August, October, December, 30 days, April, June, September, November, 28, 29 days, February, leap year check required. Since we cannot use if, we must use arithmetic and the power of the logical operators and or and comparison operators, greater than equal to, lesson 2.06 and 2.07, which result in 1 true or 0 false, to build a formula. 2. The solution strategy. We will use a combination of 3 variables to represent the 3 possible results, 31, 30, or 28, 29, and multiply them by a Boolean expression that evaluates to 1 only when that result is the correct one. The final answer will be the sum of these 3 calculated parts, where only one of the parentheses yields a non-zero value. 3. Step-by-step logic implementation. We start by setting up the input for month and year. Step A. Calculating days in February, 28 or 29. We need the leap year logic, lesson 2.10. Exercise 5. A year is a leap year if year mod 4 is equal to 0 and year mod 100 is not equal to 0, or year mod 400 is equal to 0. We can use this logic to directly calculate whether February has 29 days, result 1, or 28 days, result 0. Step B. The 31-day rule, odd, even trick. Most 31-day months, excluding August, are odd-numbered 1, 3, 5, 7, 9, 11, or August 8, and December 12. We use the modulus operator to check if the month is odd or even. Odd months, 1, 3, 5, 7 month mod 2 is not equal to 0 is true 1. Even months, 4, 6, 9, 11 month mod 2 is not equal to 0 is false 0. We combine this with the month number to get a clean Boolean result. Step C, the final formula. Now we combine all the logic into one final, non-conditional expression. 4. Complete code and key takeaway. This solution uses the power of C's Boolean evaluation, true equals 1, false equals 0, to selectively activate the correct number of days without relying on any if statements. Loop, Part 1 Basics, Exercise 1. 1. The problem review and the necessity of looping. We are starting our new section. Loops. The first problem is Exercise 1. Input a positive integer n. Calculate the sum s, n, where s, n, equals 1 plus 2 plus 3 and continues up to n. A program needs a loop to efficiently repeat an action many times. This structure prevents us from writing code manually for every single number, especially if n is large. 2. Setup and key variables. We need 3 variables for any summation loop. N, the integer input, the final limit. Sum, the accumulator variable which starts at 0. We use long for safety. I, the iterator or counter variable which starts at 1. 3. The core logic, the while loop. We use the while loop, ensuring we include the 3 essential components. 4. Logic trace, example. N equals 5. Let's trace the loop for the input n equals 5. Start. Sum is 0, I is 1. I equals 1. 1 is less than or equal to 5, true. Sum becomes 1. I becomes 2. I equals 2. 2 is less than or equal to 5, true. Sum becomes 3. I becomes 3. I equals 3. 3 is less than or equal to 5, true. Sum becomes 6. I becomes 4. I equals 4. 4 is less than or equal to 5, true. Sum becomes 10. I becomes 5. I equals 5. 5 is less than or equal to 5, true. Sum becomes 15. I becomes 6. End. The condition 6 is less than or equal to 5 is false. The loop terminates. The final output is 15. This simple loop structure efficiently solves the problem for any value of n. Exercise 2. 1. The problem review and the core change. Our next problem is Exercise 2. Input a positive integer n. Calculate the product s, n, where s, n, is equal to 1 multiplied by 2 multiplied by 3 and continuing up to n. This product is also known as the factorial of n, written as n. The structure of the solution is almost identical to the previous summation problem, but with 2 critical changes. Operation. We switch from the addition operator to the multiplication operator. Initialization. The accumulator variable must start at 1, not 0. 2. Setup and the key variable change. If we initialize the product variable to 0, the multiplication inside the loop will always result in 0, because anything multiplied by 0 is 0. Therefore, the accumulator must start at 1. We will use the variable name product instead of sum for clarity. 3. The core logic, the while loop. The structure is the same. Initialize I to 1, loop while I is less than or equal to n, and update I by incrementing it by 1. The only change is the operation within the loop body. 4. Logic trace, example. N equals 5. Let's trace the loop for the input n equals 5. Start. Product is 1, I is 1. I equals 1. 1 is less than or equal to 5, true. Product becomes 1 times 1 equals 1. I becomes 2. I equals 2. 2 is less than or equal to 5, true. Product becomes 1 times 2 equals 2. I becomes 3. I equals 3. 3 is less than or equal to 5, true. Product becomes 2 times 3 equals 6. I becomes 4. I equals 4. 4 is less than or equal to 5, true. Product becomes 6 times 4 equals 24. I becomes 5. I equals 5. 5 is less than or equal to 5, true. Product becomes 24 times 5 equals 120. I becomes 6. End. The condition 6 is less than or equal to 5 is false. The loop terminates. The final output is 120. Exercise 3. 1. The problem review and the operation. Our next challenge is exercise 3. Input a positive integer n. Calculate the sum s, n, equals 1 squared plus 2 squared plus 3 squared, continuing up to n squared. This problem is a combination of the first two. It's a summation, so our accumulator, sum, must start at 0. The repeated operation inside the loop is now calculating the square of the current number, I times I, before adding it to the total. 2. Setup and variable initialization. The setup is identical to our first summation problem. We need n for the limit, sum for the result, and I for the counter. 3. The core logic, the while loop and squaring. The loop structure remains the same, but the calculation inside the body is where we implement the squaring. In C, we calculate a square by simply multiplying a number by itself, I times I. 4. Logic trace example. N equals 3. Let's trace the loop for the input n equals 3. Start. Sum is 0, I is 1. I equals 1. 1 is less than or equal to 3, true. Sum plus equal 1 times 1 equals 1. I becomes 2. I equals 2. 2 is less than or equal to 3, true. Sum plus equa, 2 times 2, equals 4. Sum is now 1 plus 4 equals 5. I becomes 3. I equals 3. 3 is less than or equal to 3, true. Sum plus equal, 3 times 3, equals 9. Sum is now 5 plus 9 equals 14. I becomes 4. End. The condition 4 is less than or equal to 3 is false. The loop terminates. The final output is 14. Exercise 4. 1. The problem review and the modulo trick. Our goal in exercise 4 is to input a positive integer n and output all even values in the range from 1 to n. This problem requires two structures working together. The loop, to check every number from 1 up to n. The conditional check. Inside the loop, we use an if statement and the modulo operator to check if the current number is even. Remember, a number is even if dividing it by 2 leaves a remainder of 0. 2. Setup and initialization. We need integer variables n for the limit and I for the counter, starting at 1. 3. The core logic, loop, and condition. We use the while loop for repetition and the if statement as a filter. 4. Logic trace, example. N equals 5. Let's trace the loop for the input n equals 5. Start. I is 1. I equals 1. 1 is less than or equal to 5, true. 1 mod 2 is equal to 0, false. Nothing prints. I becomes 2. I equals 2. 2 is less than or equal to 5, true. 2 mod 2 is equal to 0, true. Print 2. I becomes 3. I equals 3. 3 is less than or equal to 5, true. 3 mod 2 is equal to 0, false. Nothing prints. I becomes 4. I equals 4. 4 is less than or equal to 5, true. For mod 2 is equal to 0, true. Print 4. I becomes 5. I equals 5. 5 is less than or equal to 5, true. 5 mod 2 is equal to 0, false. Nothing prints. I becomes 6. End. The condition 6 is less than or equal to 5 is false. The loop terminates. The final output is 2, 4. Exercise 5. 1. The problem review and the divisor rule. Our goal in exercise 5 is to input a positive integer n and list all of its divisors. What is a divisor? In mathematics, a number I is a divisor of n if n can be divided by I with a remainder of 0. This immediately tells us we must use the modulo operator. The loop structure will be loop. Check every number I starting from 1 up to n. Condition. Use if n mod I is equal to 0 to check for a 0 remainder. Action. If the remainder is 0, the number I is a divisor, so we print it. 2. Setup and initialization. We need integer variables n for the input number and I for the counter, which will serve as our test divisor. 3. The core logic, loop, and modulo check. We use the while loop to ensure we test every single number from 1 up to n. 4. Logic trace example. N equals 6. Let's trace the loop for the input n equals 6. Start. I is 1. I equals 1. 6 mod 1 is equal to 0, true. Print 1. I becomes 2. I equals 2. 6 mod 2 is equal to 0, true. Print 2. I becomes 3. I equals 3. 6 mod 3 is equal to 0, true. Print 3. I becomes 4. I equals 4. 6 mod 4 is equal to 0, false. Remainder is 2. I becomes 5. I equals 5. 6 mod 5 is equal to 0, false. Remainder is 1. I becomes 6. I equals 6. 6 mod 6 is equal to 0, true. Print 6. I becomes 7. End. The condition 7 is less than or equal to 6 is false. The loop terminates. The final output is 1, 2, 3, 6. Exercise 6. 1. The problem review and logic synthesis. Our final basic loop challenge is exercise 6. Input a positive integer n and calculate the sum of its divisors. This is essentially the combination of two previous exercises. Finding divisors, exercise 5, we use the if n mod I is equal to 0 check inside the loop. Summation, exercise 1, we use an accumulator variable, sum, initialize to 0 and add to it inside the conditional block. 2. Setup and initialization. We need 3 variables. N for the input, I for the counter, test divisor, and sum to hold the running total. 3. The core logic, loop, condition, and accumulation. We iterate through all numbers from 1 to n. The if statement determines if the current number I is a divisor, and if it is, the summation happens immediately inside that block. 4. Logic trace example. N equals 6. Let's trace the loop for the input n equals 6. The final output is 12. Part 2, Advanced. Exercise 1. 1. The problem review and the decomposition trick. Our challenge in exercise 1 is to input a positive integer n and output all of its digits in reverse order. For example, 123 becomes 3, 2, 1. The hint is the key. We must repeatedly use the modulo operator, mod 10, and integer division, over 10. This two-step process allows us to peel off the digits one by one. 2. Setup and the loop condition. We need 2 variables. N for the input number, which we will modify, and digit to store the result of the modulo operation. The loop must continue as long as n is greater than 0. Once n becomes 0, after all digits have been peeled off, the process stops. 3. The core logic, loop, modulo, and division. Inside the while loop, we execute the 2 crucial steps for every digit. 4. Logic trace example. N equals 123. Let's trace the loop for the input n equals 123. The final output is 321. This method perfectly separates the digits of any positive integer n, and it's the most common way to analyze the components of a number in programming. The next exercise, Advanced Exercise 2, is a variation of this. We'll use this same structure but add a condition to filter out only the even digits. Are you ready? Exercise 2. 1. The problem review and logic filter. Our challenge in exercise 2 is to input a positive integer n and output only the even digits found within it. We reuse the core digit decomposition loop we just learned. Extraction. Get the last digit using the modulo operator, mod 10. Modification. Remove the last digit using integer division, over 10. The new requirement is the filter. After extracting a digit, we must check if that digit is even. We do this using the modulo operator again. If digit mod 2 is equal to 0. 2. Setup and initialization. We need integer variables n for the number and digit to hold the extracted value. 3. The core logic: loop, extraction, and filtering. The if statement is nested inside the while loop, allowing us to filter every digit as we extract it. 4. Logic trace. Example: n equals 1234. Let's trace the loop for the input n equals 1234. The final output is 42. By combining the digit extraction loop with a conditional filter, you gain powerful control over number analysis. Exercise 3. 1. The problem and the floating point trap warning. Our task is to calculate the sum s, n, equal to 1 plus 1 divided by 2 plus 1 divided by 3, continuing up to 1 divided by n. The most important concept here is the floating point trap. If we use integer types for the division, e.g., 1 divided by I, C will perform integer division, and any result less than 1, like 1 divided by 2, will be truncated to 0. To get the correct decimal answer, we must declare the sum variable as a double for real numbers. Force the division to be a floating point operation by writing double 1 over I. 2. Full C code implementation. We will use a while loop to iterate from I equals 1 up to n. 3. Step-by-step logic explanation. Initialization. We use double sum equals 0.0 to correctly accumulate the decimal fractions. The counter I starts at 1. The division. The line of code sum equals sum plus double 1 divided by I is the core of the solution. The typecasting double forces the division to use floating point rules, ensuring accurate results, e.g., 0.5 instead of 0 for 1 divided by 2. The output. We use the format specifier %.6lf to display the result as a double, formatted to 6 decimal places, matching the example output. Exercise 4. 1. The problem review and the series formula. Our final advanced challenge is exercise 4. Input a positive integer n and calculate the sum s, n, equals 1 plus 1 over 3 plus 1 over 5, continuing up to 1 over 2 times n plus 1. The main logic requires 2 key components. Data type. The sum must be a double to handle the fractions. Loop logic. We generate the odd denominators using the formula 2 times I plus 1, where our counter I starts at 0 and goes up to the input n. 2. Setup and variable initialization. We need 3 variables: n for the limit, sum for the result, and I for the counter. 3. The core logic, loop, and formula. The loop continues as long as I is less than or equal to n. We calculate the odd denominator using the formula 2 times I plus 1 inside the loop. 4. Logic trace. Example: n equals 2. Let's trace the loop execution for the input n equals 2. For the input n equals 2, the final result is 1.533333. Exercise 1. 1. The problem review and the simulation approach. The sock problem asks, given n pairs of socks and a new pair arriving every m days, how many days until the stock runs out? We cannot solve this directly with a simple arithmetic formula because the stock change is dynamic. Every day we lose 1 pair, but periodically we gain 1 pair. The correct way to solve this is to simulate the process using a while loop that iterates through the days. The loop will continue as long as the sock stock n is greater than 0. 2. Setup and key variables. We need 3 integer variables: n, the current number of sock pairs, the stock, m, the period after which a new pair arrives, days, the counter for the total time elapsed, initialized to 0. 3. The core logic, the simulation loop. Inside the loop, we simulate the events of a single day. 4. Logic trace. Example: n equals 2, m equals 2. Let's trace the loop for the input n equals 2, m equals 2. The loop stops on day 3 when the stock finally hits 0. The output is 3. Exercise 2. 1. The strategy, the left-to-right loop. The correct way to solve this with a loop is to process the number from left to right. We will use a long variable called scale_divisor, which will represent 1 billion, then 1 million, then 1,000. A while loop will divide this scale_divisor by 1,000 in each iteration, moving us from the billions block to the millions block, and so on. 2. Full C code implementation. Three. Logic explanation. Trace the loop for n equals 2,147,483,647. Find scale. The code first finds the starting scale_divisor. For 2.1 billion, the starter is 1 billion. Main loop, iteration 1, billions. Scale_divisor is 1 billion. Current underscore block equals n over 1 billion. Result is 2. The 3-digit logic runs on 2. It prints 2. The scale logic runs. It prints billion. N becomes the remainder, 147,483,647. Scale_divisor becomes 1 million. Main loop, iteration 2 millions. Scale_divisor is 1 million. Current underscore block equals n over 1 million. Result is 147. The 3-digit logic runs on 147. It prints 147. The scale logic runs. It prints million. N becomes the remainder, 483,647. Scale_divisor becomes 1,000. Main loop, iterations 3 and 4. The loop repeats this exact process for thousands, 483, and the last block, 647.